All right, I am back for part two of today's lesson. Now we're going to talk about similar figures. Now that we've talked dilations, if I have a shape that has been dilated, like for example this cute horse, we have the small original picture of the horse and the larger dilated image of the horse. Those two shapes are called similar figures. In layman's terms, we would just say that they are two shapes that are the same shape but have a different size, where all their proportions match. So today we're going to talk about properties of similar figures, how this applies to specifically triangles and what shortcuts we can use, and then how we can solve proportions as a way to fill in missing pieces of similar figures. So go ahead and grab your guided notes and find where we left off. If you flip to the next page, you should see this. Let's talk a little vocabulary to start. So two polygons are considered to be similar if their corresponding sides are proportional. Which means they have a consistent scale factor. We talked about scale factor in our last video. On top of that, all the corresponding angles in two similar figures will always be congruent. So we can use this definition to decide if two figures are in fact similar. So I'm always going to check these two things. So I'm going to look at this quadrilateral and this quadrilateral, and I'm going to check to see are all the corresponding angles congruent. And we have the markings here indicate these two are congruent, these two are congruent, angle F and angle T are congruent, and angle E and angle S are also congruent. So we do have congruent angles here, so check mark there. Now I'm going to check all the sides and see if they have the same ratio or if they have the same scale factor. So I'm looking at the ratio from the small figure to the large figure, and the ratio there to go from 3 to a side length of 4, I would multiply 3 by 4/3. Notice if you multiply 3 by 4/3, you will get 4. Now I'm going to check, does that work with all other corresponding sides? And in fact, it does. If you take 6 times 4/3, you will get 8. If you take 6 times 4/3, you will get 8. If you take 3 times 4/3, you will get 4. Because there is a consistent scale factor here, and all the angles are congruent, I can say these two figures are similar. So it did ask for what is the scale factor. Well, the scale factor here I just found. The scale factor is 4/3 when we're going from the small figure to the large figure. Over here with these rectangles, right away I can see that the first part of my definition is good. I have 1, 2, 3, 4 right angles and then 4 right angles here. So obviously all the angles are congruent to one another. So now I'm going to check the side lengths to see if they are proportional. Now we have to be careful here, it's corresponding side lengths. So MN has a side length of 4, that corresponds with this side, UT, which is a side length of 3. So the ratio between these sides is 4:3. Does that ratio hold? Well, we look at the other side, 10, and it's corresponding to side length of 8. So the ratio from this side to this side is 10:8. Are those two ratios equal? And the answer is no. 4/3 is not the same as 10/8. So we would say no, these two shapes are not similar. The angles were congruent, but the sides were not proportional. We can check the last example here. Again, I'm going to look at the angles. Angle K congruent to Q, angle J congruent to P, angle L congruent to angle R. So check, the angles there are congruent. So now let's check the corresponding side lengths. Again, make sure you're looking at the sides that correspond. So if we look at the hypotenuse of this triangle And the hypotenuse of this triangle, notice the length has been cut in half. Scale factor times 1/2. Is that the same for the other corresponding sides? We look at 30 and 15. Yes, 30 times 1/2 is 15. We look at 16 and 8. Yes, 16 times 1/2 is 8. So we have congruent angles, and we have a consistent scale factor. From the large shape to the small shape, the scale factor here would be 1/2, or 0.5. All right, and so that is our definition of similarity. We're looking to see, do we have 4 congruent angles, or are all the angles congruent? It doesn't have to be 4, just however many angles the shape has. And are all the corresponding sides proportional? So that is for any shape. Your shape could be a quadrilateral, could be a pentagon, could have any number of sides. We can follow that rule to decide if they're proportional, to see if they're similar. If we stick to only triangles, there are a few shortcuts here. So just like when we showed that triangles were congruent and we had shortcuts, we can also show that triangles are similar with some shortcuts. Now please keep in mind that this is only, what we're going to talk about on this slide is only for triangles. But these shortcuts I'm going to show you do not work for other shapes, only for triangles. I'm going to introduce to you a little notation here. When we talk about similar figures and similar triangles, we have a new symbol. So let's say I had some triangle. Let's say it was triangle GEO. And I wanted to say that that triangle is similar to, let's say, triangle ALG. The symbol that we use just looks like this. It's one little squiggle, right? It's kind of like the top of the congruency symbol has that little squiggle there, but if we were to take away the equal sign and just had that squiggle, that means similar to. So we would read this as triangle GEO is similar to triangle ALG. Now when we're looking at two triangles, what's nice about triangles is we don't need to check all 3 angles and we don't need to check all 3 sides. There are just a couple combinations that if we have, we can stop there and we can say that these triangles are in fact similar. The first shortcut is called angle-angle, or just AA for short. If we have 2 triangles and I am able to show that one angle is congruent to another, and a second angle is congruent to a second angle, I can stop right there. I don't even need to check the third angle. I don't need to check any of the sides because I have angle E congruent to angle L, and I have angle G congruent to angle A, then I can say these 2 triangles are congruent by angle-angle. And again, I could say triangle GEO is similar to triangle ALG by angle-angle. I'm using the angle-angle similarity shortcut. For side-angle-side, that sounds familiar. We talked about side-angle-side with congruent triangles. Now that we're talking about similarity, when we talk about sides, when we see this S right here, we're no longer talking about congruent sides, we're talking about proportional sides. So for example, let's say I had these 2 triangles, and I had angle E congruent to angle L again. But maybe that's the only angle I knew. But I also knew something about the side lengths. Let's say this side was 3, and this side was 1.5. The scale factor here, from the big shape to the small shape, is 1/2, or multiplying 3 by 1/2 to get 1.5. If I knew another side that was, let's say, 4, and this side was 2, I have another pair of sides that are also in that same proportion. 3 times 1/2 is 1.5, 4 times 1/2 is 2. I would say both pairs of these sides are proportional. So notice we have a pair of proportional sides, here and here. We have a pair of congruent angles here and here. And we have another pair of proportional sides here and here. And that pair of congruent angles is in between the two pairs of proportional sides. That is enough. I can stop right there. That is enough for me to be able to say that the triangles are similar. And again, I could say that triangle GEO is similar to triangle ALG by side angle side. The side angle side similarity shortcut. Maybe we don't know anything about the angles at all, but I have three side lengths. Let's say this is 3, this is 2, and this is 4. And over here we have 1.5, 1, and 2. I can look at all three pairs of sides and ask myself, are they all in the same proportion? Do we have the same scale factor? And once again, the answer here is yes. The scale factor from 3 to 1.5 would be a half. Multiply 3 times a half to get 1.5. 2 times a half is 1. 4 times a half is 2. The scale factor here for all three sides is 1/2. If all three pairs of corresponding sides are proportional, I can stop right there and say the triangles must be similar by side, side, side. So again, I can say triangle GEO is similar to triangle ALG by side, side, side similarity shortcut. Okay. Now that we have some shortcuts, let's apply this to some problems. Next example here, we are going to first determine which similarity shortcut proves that the triangles are similar, and then we're going to use the fact that the triangles are similar to solve for A, B, and X. So first things first, let's look at, we'll call this number 1 here. Which similarity shortcut proves each pair of triangles are similar? Well, let's look at the information we're given. In the first example, I notice I have some angle markings. This angle is congruent to this angle here. This angle with the double lines is congruent to this angle here. So I have two pairs of congruent angles. And right there, I can stop. Right? Once I've shown, if I have triangles and I've shown I have two pairs of congruent angles, I know that these triangles are similar by the angle-angle shortcut. Now the question is, how can I figure out the measure of side length A and side length B? To do this, I'm going to connect these problems back to something we were doing last week, which was solving proportions. I can look, now that I know these two shapes are in fact similar, I can find a pair of corresponding sides and determine what the ratio between the sides is. This side length of 9 corresponds to this side length of 15. I know that by looking at the angles, right? So 9 is in between this angle and then this angle that has no marking here. 15 is between the same two angles on this triangle, right? So those two sides correspond. So the ratio of the small triangle to the large triangle is 9/15. That means all the other corresponding pairs of sides will be in that same ratio because we already know that the triangles are similar. So if the ratio is 9/15, that will be the same as the ratio of A to 12. The ratio of A to 12. And these ratios must be equal to each other. Hey, look at that. That is called a proportion, which we know how to solve. Last week I showed you guys the cross multiplication shortcut here, which I'm going to use. So I'm going to do 15 times A, and I'm going to do 9 times 12, and we turn our two fractions into an equation that no longer has any fractions. And when we solve here, dividing by both sides by 15, we get 7.2. And I'm going to use the same technique now to solve for B. The The side length B corresponds to side length 10. We can use the same starting ratio that we knew. The ratio of the two sides is 9 over 15. That ratio should be equal to the ratio of these two corresponding sides, B over 10. Notice my order stays the same, right? If I do 9 over 15, I'm doing the left triangle over the right triangle. I'm going to follow that same order, and I'm going to do the left triangle over the right triangle, B over 10. Make sure that order is consistent to set up your proportion, but again, once you have your proportion, we can just cross multiply and solve. 9 times 10 is 90, 15 times B is 15B. Set those equal, and divide both sides by 15, and we get that B is equal to 6. Move on to the next example. Again, I'm looking at these two triangles, and I see a pair of angles congruent here, another pair of angles congruent here. Again, I can stop right there. I know these two triangles must be similar using the angle-angle shortcut. So now, to find x, I'm going to write and solve a proportion. Again, we want to make sure we match up corresponding sides. Just like in the previous example, this side length 4 corresponds with this side length 10. So the ratio between these two sides is 4 to 10. That ratio will be the same for all corresponding sides. So the ratio between this side, x, and this side, 2x plus 3, will be in that same ratio. So 4 over 10 is equal to x over 2x plus 3. These ratios must be the same. Hey, now we have another proportion, and we can solve. We need to do a little more algebra here. 10 times x, 4 times 2x plus 3, and now we're just solving. And we get x equals 6. Okay. Now we have talked about how to determine if triangles are similar using one of the three shortcuts. Once we know they're similar, we can now solve for missing sides using proportions, where we just match corresponding sides to one another, and we know they have to be in the same proportion, and that lets us create an equation. If you look at the next three examples in your guided notes, you are asked to determine whether the triangles can be proven similar, and if they are similar, to write a similarity statement, and if they are not similar, to explain why. Now would be a good time for you to pause the video and try these two examples you see on the screen, and then there's two more examples in your guided notes that look like this, and you can try those as well. So try those 4 examples. When you're finished, come back to the video, unpause me, and I will go through and show you the solutions. So go ahead and pause now and try those 4 examples. And we're back. Okay, let's take a look at these problems here. Now, here we have some overlapping triangles. I noticed right away that I'm not given any information about the side lengths. So we're really going to be looking at angles here. In the small triangle, I have 85, 60, which allows me to find this third angle that would have to be 35. In the larger triangle, this large triangle here, I have an angle of 85, another angle of 30, which lets me get this angle here, that's 65. So when I compare these two angles, or excuse me, these two triangles, I notice that my angles are not the same. They do share this angle of 85 degrees, but this angle is 60, which corresponds to this angle of 65. They're not congruent. 35 here and 30 here, they're not congruent. So we would say these triangles are not similar. Why? Because the angles are not congruent. The next example, we have, again, nothing about the side lengths, but we are shown that we have some congruent right angles here. And we have some parallel lines. Now, those parallel lines are going to allow us to say something about this image. Because if these lines here are parallel, then this other segment, AC right here, acts like a transversal, which means these angles must be congruent. They are what we call corresponding angles. Right there, I can stop. I have one pair of congruent angles. I have another pair of congruent right angles. I can say that yes, these triangles are congruent by the shortcut angle. My similarity statement would be to say that triangle ABD is similar to triangle BCE by angle. Take a look at the next couple. Again, in this third example, we're just looking at some angles, and we do have a pair of side lengths here. So let's investigate this a little bit more. I'm going to fill in some missing information. So if this is 90 and 45, then this also has to be 45. And over on this triangle, if this is 54 and 45, this angle has to be 81. Now, I'm going to stop right there. We do have some side lengths that we could investigate, but I don't really need to. I'm checking to see if the sides are, if the angles are congruent, because if the angles are not congruent, I can stop right there, and I know that these shapes are not similar, and that's exactly the case. 45, 45, and 90 does not match 45, 54, and 81. So again, we can stop right here and say these are not similar. The angles are not congruent. Okay, last one. Let's look at what we have here. So we have side lengths in this case, but no angles to look at. So that means I'm going to start comparing the side lengths and see if we have the same proportion, if we have the same scale factor. So let's find the pieces that correspond. And that's real important here, is that you have to match up the corresponding sides. So MN, this length of 6 right here, corresponds to this side SR, which is a length of 9. So if I'm comparing the small shape to the large shape, I'd say the ratio there is 6 to 9. Let's find another pair of corresponding sides. How about 8 and 12? So this side, here I'll use a different color. So this side here corresponds with this side here. Be consistent in your order. Since we did 6 over 9, now we can do 8 over 12. And compare those two. Let's look at the third pair of sides, 4.5 and 6.75. The ratio between those two sides, 4.5 over 6.75. And now I'm going to ask myself, are these three ratios equal? And in fact they are. 6 over 9 is the same as 8 over 12, which is the same as 4.5 over 6.75. You could use a calculator to confirm that. Because all three sides are proportional, I can say yes, these triangles are congruent by the similarity shortcut side, side, side. My similarity statement would be that triangle OMN is similar to triangle QRS by side, side, side similarity shortcut. Okay, that brings this video to an end. You should now have all the information you need to try the homework assignment that I've posted there. I also have posted an answer key so you can check your work. I hope this was helpful. Until next time, you guys enjoy your week.